What's up, my pre-calc people? I'm Michael Porinchak, and in this video we're going to tackle AP Precalculus topic 1.5 on polynomials in complex zeros. The zero of a polynomial is perhaps one of the most important points you can identify, and sometimes it could be real, and sometimes it could be, well, part real, part non-real. That makes it a complex number. So let's learn all about how to find these complex zeros of a polynomial function and what you have to do to make sure you understand them.
So if we're going to talk about polynomials and complex zeros, we should probably do a quick recap about what the heck a complex number is. So a complex number extends the real number system into the imaginary number system with the letter I. Now I'm not going to go over all about I, but hopefully you guys remember that I is equal to the square root of -1. Now a negative inside of a square root is non-real. That's not going to show up on any graph, and that's the whole idea of why we call it imaginary. Now complex numbers have a real part, which we generically call A, and an imaginary part, which we generically call B. They're written in the form like this, A plus BI, where A is the real part and B times the I is the imaginary part. Now, there can be no real part A, or there could be no imaginary part B, or there could be some of both. So, for example, 7, the real number 7, is technically a complex number if we write it as 7 plus 0i. So 7 is, of course, the real part, and there is no imaginary part, but we could represent that no imaginary part with the 0i. 6i is also a complex number. It has no real parts. We can represent that real part with a 0, and it does have an imaginary part, 6i. Or we obviously might have a combination here where we have 7 minus 5i that has both a real part 7 and an imaginary part -5i. Now, I realize that was like the fastest recap ever of what a complex number is, but basically we're in a unit for AP Precalculus called polynomials and complex zeros. We have to understand that when we talk about complex zeros, we talk about real zeros, imaginary zeros, or maybe a combination. So any number in the real number system can be made into a complex number if we just tag on that 0i. So that's why we want to talk about complex numbers when we also want to talk about the zeros of a polynomial function. All right, so if C is a complex number and P of C equals 0, then C is called a zero of the polynomial function P, or a root of P of X equals 0. If C is a real number, then X minus C is a linear factor of P if and only if C is a zero of P. Okay, I know that was a lot right there. That's a pretty big standard from the AP Precalculus curriculum, but let's dive into that a little bit more. Here's the idea. Polynomials can have real zeros or complex zeros involving imaginary numbers. Not every zero of a polynomial is going to be real. Now, obviously, on a graph, you're only going to see the actual real ones, but there's also these complex zeros that aren't going to show up on a graph if they're imaginary parts. So let's look at a couple examples to actually break down what this standard is saying. So, for example, we know that we have a 0 at C. Okay, great. That simply means a couple things. If we plug C into the polynomial, we're going to get 0. I mean, that's the definition of a 0. You plug it in, you get 0. That also means that X minus C is a linear factor of the function. Okay, X minus C is a linear factor of the function. You should have learned that back in Algebra 2, to be honest. And the other thing we know is that if we look at a graph of this function, we're going to see an x-intercept at C, 0, where the graph crosses the x-axis. But if it's involving an imaginary part, if there's any imaginary parts of that complex number, you actually will not see an x-intercept because x-intercepts only occur at real zeros. So let's look at a couple examples here. So if 5 is a 0 to a polynomial P of X. Here's what we know. We know that when we plug 5 into the function, we're going to get 0. We know that X minus 5 is a linear factor of P of X. Now I want to make sure it's very clear here. Why is X minus 5 a linear factor? Because if we plug in 5 minus 5 is, you guessed it, 0. Now there might be other factors of this polynomial, but if one of them creates a 0, 0 times any other factor is going to turn the whole darn thing into 0. And we also know that there is a x-intercept at 5, 0 on this graph. All right, here's another example with x equal -7 being a 0. Again, that means when we plug -7 into the function, we get 0. X plus 7 is a linear factor because if we plug in -7 plus 7, we get 0, making the factor 0, which is going to turn the whole polynomial into 0. And we also know we're going to see an x-intercept at -7. All right, but what if we have a imaginary part to this complex number, and let's say that 2 plus 3i is a 0. Now that's going to be a complex 0 because it's got a real part and an imaginary part. All right, well, that also means if we were to take 2 plus 3i and plug it into the function, we will get 0. And that also means that x minus 2 minus 3i is a linear factor. Now, it's not going to be real, but it's still considered a factor. Now, where are we getting the x minus 2 minus 3i? Well, remember, we're plugging 2 plus 3i in for x. So the 2 and the minus 2 are going to turn into a 0, and the positive 3i and the negative 3i are going to turn into a 0, so the entire factor becomes 0, making the entire polynomial 0. Now, this will not create an x-intercept on our graph because it has an imaginary part, and if there's an imaginary part, well, it's not a real 0. It's not a real 0 that you're going to see. It's a complex 0, but it's not a real 0, so we're definitely not going to see an x-intercept there. Now, this actually brings up another good standard that is taught in this particular topic, and that is if a plus bi is a non-real 0 of a polynomial function, then its conjugate a minus bi is also a 0 of p. So here's the deal. These non-real zeros that are complex, they come in what we call conjugate pairs. So if a plus bi is a known non-real 0, then automatically a minus bi is another known non-real 0. So for example, if 5 minus 2i is a 0, then 5 plus 2i, well, that's not a 5, 5 plus 2i is automatically a real 0, a non-real 0 as well. Or if negative 3 plus 4i is a known non-real 0, then negative 3 minus 4i is another one. So again, it's only the sign in the middle that changes. So if this 5 is positive, then this 5 is still positive. It's the imaginary part that's minus 2i or plus 2i. Negative 3 and negative 3 stay the same. It's the imaginary part that changes from positive 4i to negative 4i. All right, so if we look at that last problem we just got done talking about, we said 2 plus 3i is a 0. Well, that immediately means that 2 minus 3i is another 0, non-real 0. Again, that rule is only true for non-real zeros. So again, we already determined that 2 plus 3i is 1, so now we know 2 minus 3i. So once again, what does that mean? Plug 2 minus 3i in, we get 0. X minus 2 plus 3i is a linear factor, and, well, there's not going to be any x-intercepts because, well, it's non-real, if it's non-real. Now, some people will say that x minus 2 plus 3i is not officially a linear factor because it involves an imaginary part, but it's still a factor of the function, and we're going to talk about that and kind of demonstrate that in a couple moments here. All right, so here's one more tidbit before we start looking at some solid examples. If a linear factor x minus a is repeated n times, then the corresponding 0 of that polynomial function has a multiplicity n. So if we repeat the same linear function n times, then we say that that linear factor has a multiplicity of n. So a polynomial function of degree n has exactly n complex zeros when counting multiplicities. So basically, just to, long story short here, if we have x minus 2 to the third, well, we only have one 0. That 0 is x equals 2. Plug in 2, you get 0. But it's repeated 3 times, so we say it has a multiplicity of 3. And that's going to actually matter when we talk about a couple more important things later on. But let's start looking at some examples. Now, for the AP Precalculus exam, you need to be able to look at some mostly quadratics, but we'll expand on that in a moment. And you have to be able to look at these polynomials, in this case it's a quadratic polynomial, and find, well, the real zeros. So how are we going to do that? Well, if we are allowed to use our calculator on this particular problem, we could simply look at a graph and we could locate the zeros, or we could use the solving capabilities of a calculator and actually get the zeros. But if you can't, well, then you're going to have to factor or use the quadratic formula by hand. But this one should factor. So if we're trying to figure out where this function is equal to 0, we're going to set it equal to 0 and we're going to factor. All right, how do you factor? Well, there's only one way in the world to break apart a 2x squared. That's going to be a 2x and an x. Now, how do you break apart a 12? Well, the first thing that pops in my mind is 4 and 3, but I could also do any combination of 6 and 2. All right, now I do need it to be a negative 12, so one of those factors is going to have to be a minus. So let's just try one out here. So maybe we put a minus 3 here and a plus 4 here. So now this is guaranteeing me that 2x squared in the front, and it's guaranteeing me that negative 12 in the back. Now I got to figure out, am I going to get a positive 5x in the middle? Well, when I multiply the outsides, I'm going to get an 8x. Okay, that's awesome. When I multiply the insides, I'm going to get a negative 3x. And I can't believe it, I guessed right on the very first time. That's going to create that 5x in the middle. So those are the correct factors. But be careful if you tried some other options and it didn't work. Maybe I should have tried one that didn't work so you could see it. But again, you're trying different ways that you can incorporate the 4 and the 3 or the 6 and the 2 that's going to generate the 2x squared in the front, negative 12 in the back, and that 5x in the middle. Looks like I found on the first try. All right, so looks like I got some linear factors. This means that x equals 3/2 is a known zero, and x equals negative 4 is a known zero. Hopefully I didn't go through that math too quickly there. I know you guys know how to add 3 and divide by 2 or subtract 4. So I got 2 zeros. If I plug them in, I'm going to get 0. If I look at a graph, I'm going to actually see some real zeros, some x-intercepts at those 2 values. All right, now here's another one. And we could also factor this one as well. So we're going to set it equal to 0. We're going to go ahead and get our factors. So I have x times x. That's the only way to break apart and get this x squared right here. When I think of 16, I got 8 and 2, 4 and 4, 16 and 1. But the first thing that pops into my mind is 4 and 4. And let's see if this works out here. So 4 times 4 is 16. If I make them both positive, when I get that 4x on the outside and that 4x on the inside, I'm going to generate that 8x in the middle. So this is perfect. But I could also rewrite this as x plus 4 squared, because it's just x plus 4 times itself, which again can be shortened to x plus 4 squared. So I really only have one zero. The only zero I have is negative 4, but it has a multiplicity of 2. It's got a multiplicity of 2 because it was repeated twice. So that's really important to understand. Multiplicity of 2. Okay, now let's go back to that rule, because it's actually a really, really important rule that we said earlier. If you have a polynomial function of degree n, and I hope you guys know how to find the degree of a polynomial, then it has exactly n complex zeros when counting multiplicities. So if we look at this first problem right here, we had a degree of 2. So that automatically means I have 2 total complex zeros, including the multiplicities. And there they are, 1, 2. All right, here's another one. Degree is 2, so I better have 2 zeros, 2 complex zeros, including multiplicities. Well, I really only have one actual zero, but it has a multiplicity of 2, so that's where, again, when the rule says when you include multiplicities, then your degree matches how many complex zeros you have when you include those multiplicities. All right, let's look at another example here. This time, I'm not going to be able to factor this one, and this happens sometimes. Now, if it is a quadratic and you are allowed to use your calculator, please graph it. Please use the solving techniques on your calculator because it can get you answers fast. But I'm going to have to go ahead and use the quadratic formula here. So to get my answers, I'm going to go ahead and do the opposite of b, negative 4 plus or minus the square root of b squared, 16, minus 4 times a times c, which is 21, all divided by 2 times a. All right, now I got to figure out what is inside that square root. So I'm going to do 16 minus 4 times 1 times 29, and I get negative 100. So I get negative 4 plus or minus the square root of negative 100, all divided by 2. Now, when you get a negative inside of a square root, that merely tells you that you have no real solutions. There will not be any real solutions. I'm not going to see any x-intercepts to this graph. So what's happening, this is going to be a quadratic that's opening up, and it is already above the x-axis, so there are no real zeros. But I do have these complex imaginary zeros. Now I just got to solve for them. So I have negative 4 plus or minus. Everybody knows the square root of 100 is 10, and then the square root of a negative is the I. So basically what I'm doing is I'm separating the square root of negative 100 to the square root of negative 1 and the square root of 100. The square root of negative 1 is the I, the square root of 100 is the 10, all divided by 2. Now I could literally divide everything by 2. Negative 4 divided by 2 is negative 2. 10i divided by 2 is 5i. So there are my complex imaginary zeros. And notice they come in those conjugate pairs that we knew that would happen. So if negative 2 plus 5i is a complex zero, we automatically have another one at negative 2 minus 5i. They always come in those complex pairs. There you go. That's how simple it is. All right, here's another example. And this time we have a cubic. It's a third degree. Now, that means I'm going to have 3 complex zeros when I include multiplicities. All right, so let's go ahead and factor this. Now, on the AP exam, you're not going to have to do a whole lot with cubics, and if you can, they're going to be easily factorable. So for example, I could easily see that I could factor out a 3x, which is going to make this a pretty easy problem. I'm going to get x squared plus 3x minus 10. Now, I'm going to be able to factor that remaining quadratic part. For the AP exam, you really only need to know how to factor quadratics. If there's a cubic, you're going to have to factor out something common first, and then you're going to get a quadratic that you can factor. This is actually a pretty easy one to factor. We got an x and an x. When I think of 5 and 2, that's going to give me that 10. But I want a positive 5 and a negative 2 to get that positive 3x in the middle. So here are my 3 complex, I guess they could be considered complex, but they are real, but real numbers are also complex, just no imaginary parts. But we have x equals 0 from right there. We have x equals negative 5 from that linear factor right there, and x equals 2 from that linear factor right there. So there are my 3 factors, or my 3 zeros, including multiplicities. Now, what are the multiplicities of these? Well, they're all technically to the first. They all appear one time, so technically they all have a multiplicity of 1. All right, here's another example where we have a cubic, and you're not going to have to be able to factor cubics on the exam other than being able to factor out a greatest common factor, which in this case is just an x, leaving behind x squared minus 2x plus 5. Now, if you try to factor that remaining quadratic, you're quickly going to realize you can't. So I do have this one part right here, x equals 0. That's definitely going to be one of my zeros. But to find the other ones, I'm going to have to go ahead and use the quadratic formula again. So x equals the opposite of b, which is 2, plus or minus the square root of b squared, which is 4, minus 4 times a, which is 1, times c, which is 5, all divided by twice a, which is 2. X equals 2 plus or minus. Inside that square root, I get 4 minus 20, which is negative 16, all divided by 2. Now, once again, I'm going to stop right there. I get a negative and a square root. That means I have no real zeros from this part. I still have this real zero right here of 0, but from these remaining quadratic, I have no real zeros. But again, I could separate that 16 to a negative 1, and it's 16. So the square root of 16, everybody knows is 4. The square root of the negative 1 is I, and I get 2 plus 4i all over 2. And that's going to be 1. 2 divided by 2 is 1. 4 divided by 2 is 2i. And there's my other 2 complex zeros. 1 plus 2i and 1 minus 2i. So I got 3 zeros that are complex, including multiplicities. There it is. There's my degree 3. Here's my first. That's real. I'm going to actually see that on a graph. And then here are my other 2 complex imaginary zeros. All right. Now we also should be able to go the other way, where I give you the zeros and you determine what the polynomial function could be. So if I know that there's a polynomial function that has these 2 zeros, all I have to do is create their linear factors. If 3 is a 0, x minus 3 is its linear factor. 3 minus 3 is 0, turning it into 0. And if x minus 5 is a linear factor, is a 0, then x plus 5 is its linear factor, because negative 5 plus 5 is turning into 0. There, I'm done. I just created that polynomial. Now, of course, I can multiply it together. X squared plus 2x minus 15 to get what that actual polynomial would look like going the other direction. Now, we do have to be a little bit careful here. This is not the only answer to the problem. This is not the only polynomial in the world that has those 2 zeros. Because what I could do is I could multiply it by a constant, like 3 or negative 5 or 10 or 22 or 1/2. It doesn't matter. You can multiply it by any constant you want, and it's going to change your coefficients, but it will not change what these zeros are. So be careful in saying that that's the only polynomial that has those 2 zeros, because it's not, because I can multiply everything by a constant and it would make the polynomial be different but still have those same 2 zeros. All right, here is another example. This time we have 2 is a 0. Okay, that's awesome. So that means I have a linear factor of x minus 2. Plug in 2. 2 minus 2 is 0. But this time I have another 0, but it's complex. It's imaginary. Okay, don't panic. That just means that x plus 5 minus 2i is its linear factor. Negative 5 plus 5 is 0. 2i minus 2i is 0. That's why it turns into a 0. But don't forget our really, really important rule about complex imaginary zeros. They always come in these conjugate pairs. So if negative 5 plus 2i is a 0, I automatically know that negative 5 minus 2i is another 0, which means another linear factor would be x plus 5 plus 2i, because negative 5 plus 5 is 0, and the negative 2i and the positive 2i is going to be 0. Now, this looks really ugly, and you might be thinking, well, that can't be a polynomial. Well, actually, it can. When you multiply this out, it's going to take a minute to do, but it's actually going to work out to be kind of an innocent-looking polynomial that does have these zeros, 2 being the real 0, and then these 2 complex imaginary zeros. Now, always start by multiplying out the complex part. So I'm going to leave the x minus 2 there for a second. All right, so I got x times x is x squared. That's simple enough. X times 5 is 5x. Okay, that's still pretty easy. And then x times 2i is, well, x times 2i. Okay, then we're going to distribute the 5. 5 times x is 5x. 5 times 5 is 25. And 5 times 2i is a positive 10i. One more to go here. Distribute the negative 2i times x. So I have negative x 2i. Negative 2i times 5 is negative 10i. And negative 2i times positive 2i is going to be a negative 4i squared. All right. Sorry for kind of messing all that up. Well, my handwriting is a little bit messy, but you get the idea. All right, so now let's clean all this up. Notice that anything with an I is going to cancel. We have a 10i and a negative 10i. They turn into a 0. A positive x2i, a negative x2i. So let's see what's left. We have an x squared, we have a 5x and another 5x. That's going to make a 10x. Then we got this 25 right here. Okay, that's pretty easy. But don't forget about this minus 4i squared. In fact, I'm going to write that kind of real big over here. Let's kind of go to and analyze that. Negative 4i squared. Okay, well remember, I is the square root of negative 1. And when you square a square root, this cancels away and you just get what's inside. So I squared is equal to negative 1. So I get negative 4 times negative 1, which is a positive 4. Again, that's because the square root of negative 1 is I. So when you square it, you just get negative 1. So essentially that negative 4i squared turns into just a plain old 4. So now I have x minus 2 times x squared plus 10x plus 29. The imaginary parts all kind of mysteriously go away, and we have this, well, somewhat innocent looking polynomial. I now could distribute the x and then distribute the negative 2 across to get a cubic that's going to have one real solution at 2 and then 2 imaginary complex solutions at negative 5 plus 2i and negative 5 minus 2i. So pretty cool process. I know I didn't finish off there, but you can go and distribute that to clean that up. But again, it just goes to show that you can take these complex imaginary factors and multiply them together. All right, now here's an example where we actually already have it all factored for you, but the point of me showing you this is so you could see the multiplicity. So we have 1, 2, 3, 4 factors here. The good news is that they're all real. So x being by itself means x equals 0 is a 0. This would be 4 because 4 minus 4 is 0. This would be 5/3. Add the 5 divided by 3. Or if you plug in 5/3, 3 times 5/3 is 5. 5 minus 5 is 0. And this one right here would be negative 2. But they don't all have the same multiplicities. X equals 0 has a multiplicity of 1. It only appears one time. So I'm going to write m1, multiplicity of 1. The x equals 4 appears twice. So that's actually going to have a multiplicity of 2. So even though it appears once, it has a multiplicity of 2. It's an even multiplicity. The 5/3 has a multiplicity of 3 because it's repeated 3 times. And the negative 2 has a multiplicity of 1 because, again, it's only repeated 1 time. So it's really important that you know how to look at a polynomial and understand the multiplicities. So what's my degree? Well, add up all of your multiplicities. So I have 1, 2, 3, 4, 5, 6, 7. This is going to be a 7th degree polynomial. If I were to actually multiply all the x's out, I would end up with an x to the 7th. I got x to the 1st times x squared times x cubed times x. That's going to be in totality an x to the 7th or 7th degree. Now, understanding multiplicity is going to be important for what we're going to talk about next. If the real 0 c of a polynomial function has even multiplicity, then the signs of the output values are the same for input values near x equals c. For these polynomial functions, the graph will be tangent to the x-axis at x equals c. now most kids read this and they're like, what the heck does that say? Let me explain. If you have a linear factor, x minus c, and the multiplicity up here, right? The multiplicity is even. So we're looking at 2, 4, 6, 8, any of that. What happens is when we look at that specific zero on our x-axis, and that's a terrible x-axis I just made, but if we look at c on that x-axis, because again, c minus c is going to be 0, and that's why we see that there is a 0, right? Okay, so what this says is that signs of the output values are the same for input values near x equals c. So when we get really close to c, if the left side are positive, then the right side are also positive. The signs, positive or negative, of the output values are the same when you're near x equals c, either near on the left or near on the right. Or if the left-hand side is negative, then the right-hand side is also going to be negative. And what that means is that we don't cross at that 0, we touch, or we're tangent. That's why it says the graph is tangent at x equals c. So if I'm going to go ahead and draw my graph in here, my graph's going to come like this. It's either going to be negative, 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 up, just touch, just be tangent, and then still be negative, negative, negative. So it's still 0 right there, but on both sides, it's the same sign, in this case, both negative. Or it could both be positive. So here comes my graph, it's positive, it touches, creating that 0 at C, but on the other side, it's also positive as well. So that's what we call a tangent to the x-axis. Let me draw a little bit nicer picture here. So here'd be an example where both sides are negative. So here's C right here, left side's negative, right side's negative for values that are really, really close to it. That doesn't mean that the graph somewhere doesn't turn around and come on over here. That's somewhere else, right? We're just talking for values that are near C. The left side and the right side are going to be the same. Or one more example, and I'm drawing some really bad graphs here, but I hope they make sense to you, is maybe we're all positive, touch at that C, and then we stay all positive, something along those lines. Now, on the other side, if the real 0 C of a polynomial function has odd multiplicity, then the signs of the output values are the opposite for input values near C. For these polynomial functions, the graph will cross through the x-axis at x equals C. All right, so again, if we have x minus c, it has, that means there's a 0 at c. If it has an odd multiplicity, maybe there's a 1 right there, or a 3, or a 5, that means we're going to cross at c. So when we think about that number line, and right here is c, it's opposite. So one side is positive, one side is negative, or vice versa. So maybe the left side is positive, the right side is negative, which means the graph is going to cross through at that 0. Or maybe it's the opposite, and the left side is the negative and the right side is the positive, and again, it's going to cross through at that 0. So the multiplicity of a 0 will tell you if you're going to be tangent at that 0 or if you're going to actually cross through. So kind of, it's kind of written a little bit weird, but hopefully that makes a lot of sense. So here is back to that function that we knew that we had x equals 0 is multiplicity of 1, x equals 4 had a multiplicity of 2, x equals 5/3 had a multiplicity of 3, and x equals negative 2 had a multiplicity of 1. So this being the only even multiplicity, at 4 we're going to be tangent. We're not going to cross, we're going to touch. So both sides of 4, I wrote m equals 4, that should have been a x equals 4 there, sorry about that. The multiplicity is 2. But both sides of 4 are going to have the same sign. Right? All the other zeros, 0, 5/3, and negative 2, it has an odd multiplicity, so it's going to cross at those zeros, one side positive, one side negative. So here's an actual picture of this graph. It's kind of zoomed way out, but I want you to see this. So here we have that one negative 0 of negative 2. And remember, negative 2 had a multiplicity of 1. So when we look at the graph, notice how one side of it is negative and the other side is positive. So these values are negative, these values are positive. Another one of our zeros was 0. Okay, 0 also had a multiplicity of 1. That's odd. So again, one side is positive and one side is negative. Another one of our zeros was 5/3, and that had a multiplicity that was odd as well. It was 3. So when we see 5/3 right here, one side is negative, one side is positive, and it crosses through the graph at 5/3. But for positive 4, we see that it doesn't cross, it's tangent. The left side is positive and so is the right side. That happens when your multiplicity is even. Okay, so hopefully that makes sense. I know that those are some kind of weird rules when you have to write them down, but when I explain them, hopefully they make a lot of sense. Now, this is not it for topic 1.5 of AP Precalculus. There's also a section about solving inequalities, polynomial inequalities. I have another video for that. There's also a section on determining what your degree is if you don't actually have the polynomial in front of you, but you have a table of values. I mean, if you have the polynomial in front of you, just look at the largest exponent. But if you have a table of values, how can you determine the degree? I got another video for that. And there's even a part of 1.5 that's talking about even polynomials versus odd polynomials. What the heck is an even function versus an odd function? Well, that is also explained in a separate video. So 1.5 on paper looks kind of short, but there's a lot of really big ideas in it. So I have several videos, so please pay attention and look up those videos as well. All right, talk to you later. Hopefully you enjoyed.